Dear students, welcome to the online class. So because of the COVID situation, we have no choice but to take the classes online. In the classroom, we had discussed a lot of things in lesson 1. We talked about charges, then we did a couple of demonstrations, and we talked about Coulomb's law of attraction or repulsion, and we also talked about the electric field, which is nothing but the influence of the charge around itself. That is, if you have a charge, then the charge is going to affect any other charge which is going to be brought in the vicinity of the charge, and it seems to exert an influence on the test charge. So that is the electric field. That's what we call as the electric field of the charge. So the electric field is nothing but the influence of the charge in the space around itself. We discussed that, and we have done quite a few problems. So this is what we have done in the class. Now we will do example 1.9 as a continuation of what we have discussed so far, and we'll take this forward from there. We have done 8 problems in the class, till 1.8, 8 example problems were done. But now I'm going to focus on example 1.9, which is also part of the discussion that we have had so far. So we'll do the problem. Example 1.9. So 2 point charges Q1 and Q2 of magnitude plus 10 power minus 8 coulomb and minus 10 power minus 8 coulomb respectively are placed 0.1 meter apart. The electric fields at points A, B and C shown in figure 1.14 have to be calculated. Okay, so you need to calculate the electric fields at points A, B and C as given in the figure. So there are 2 charges basically. One has a plus 10 power minus 8 coulomb. And the other one is minus 10 power minus 8 coulomb. They are placed with a separation of 0.1 meters. And then there are 3 points that they're talking about in that picture, and you have to find the electric field at each point. So it's a very simple problem. So we'll do that now. So we're going to do example 1.9. Okay, so the charge, the positive charge is given here, so that is plus Q, and then the negative charge is given here, it's minus Q, but each of them have the same magnitude, which is 10 power minus 8 coulomb. So this is going to be plus 10 power minus 8 coulomb, and this is minus 10 power minus 8 coulomb. So you can expect a force of attraction between the 2 charges, but that is not we are interested in right now. Okay, so let's see. Now, they are separated by a distance of 0.1 meter. So that's about 10 centimeters. That's the separation between the 2 charges. Now, they want you to find the electric field intensity E due to these 2 charges at 3 places. One is at the very center. At the very center, so this is called A. This position is called A. And what is electric field intensity due to these 2 charges at A? Secondly, at B, which is again 0.05 centimeter from the positive charge. So this distance, let's say, this distance is 0.05 meters. So half the distance, right? Half this 0.1 meter. So that's B. And there is the third place, C. That is somewhere here. Okay. So the distance between this point and this position C is again 0.1 meter. And again, to that, this is again 0.1 meter. So it's like an equilateral triangle. So I need to find now the electric field intensity E due to these two charges at A, B and C. And that is the problem. Okay. You see, if I take this point is going to be influenced by both the charges. Like plus Q will influence this point or any charge kept at that point, and minus Q will also influence any charge kept at this point. So what is the net influence at that point? Okay. So that's the question. So what you need to do, like you have to find the influence due to one charge, and then you also have to find the influence due to the other charge separately, and you need to add these two influences vectorially because electric field is a vector quantity. That's all there is to it. Okay, let's try to do the influence at point A. I call that as EA. It's a vector EA. That's a net field at point A. And we know that this is equal to the influence at A due to 1, right? So at A due to 1, that's a vector, plus influence at A due to negative charge 2. Okay? We'll call this as Q1 and we'll call this as Q2. So influence due to Q1 and the influence due to Q2, and I need to add them vectorially. Okay. So to do this, what would I do? I would bring in a unit positive test charge. The charge here at this point, the charge I'm going to keep at this point A is going to be the unit positive test charge. I'm going to see what is the amount of force experienced by the unit positive test charge, and that is the value of E. Okay, so I've got a unit positive test charge here. Now, what is EA1? EA1 is going to be equal to K, then Q1 into the unit positive test charge 1 by the distance between the unit positive test charge and Q1. So that is 0.05 square. Okay. Yes, that's the distance between this point and this charge. Because the whole distance is 0.1 meter, so half of it is 0.05 meters, so square. So that's the thing. So that's the magnitude. And what would be the direction of that? So this is a positive charge, and I'm going to bring another unit positive test charge. So it is going to be in this direction. It will be repelled by this charge. So that is my EA1. See, EA1 is in that direction. Okay. So can I calculate the magnitude of this? That's easy. So what is K? K is 9 into 10 power 9 into Q1 is simply 10 power minus 8 coulomb, right? So 10 power minus 8 coulomb. And I've brought the unit positive test charge, so that is 1. That has no effect at all. So divided by the 0.05 meters square. Okay. Well, I can do some kind of a manipulation here. I can do it like this. So 9 into 10 power 9 into 10 power minus 8. I just keep it like that. Or if I add these, I mean, like if we do the operation on the numerator, then it is going to become 9 into 10 power 1. So 9 minus 8, so 10 power 1. So it's simply 90. Okay? It's divided by, so what I've got here, 0.05 square. So let me write it in a slightly different way. It's going to be equal to 0.5 into 10 power minus 1 whole square. So, okay? Because I'm multiplying it by 10 and dividing it by 10, so I'm getting 0.5 into 10 power minus 1 square. So that is going to give me 9 into 10 power 1 divided by this 0.5, I can write as half, right? Half into 10 power minus 1 the whole square. So this will become 1 by 4. Half will become 1 by 4 and that 4 will go up. So that will give me 36. 9 into 4, 36 into 10. And then the bottom you have got 10 power minus 1 square. So that is 10 power minus 2. Then when it goes up, then it becomes 10 power 2. So that gives me 3.6 into 10 power 4 Newton per coulomb. So this coulomb charge, 1 coulomb charge is going to experience this amount of force. That is my EA1. Okay. Next, we are not done, right? You need to worry about the influence due to this charge at the same point. Okay, so EA2. So the same K and then Q2 and 1. That's the charge, that's the value of the unit positive test charge. So divided by, what's the distance? Again, the distance is 0.05 the whole square. Okay. Again, what have we got here? You got 9 into 10 power 9 into this 10 power minus 8, but this is negative charge. I can put a negative sign here to get the direction also. Or if you just want the magnitude, then I can just leave that and then see which direction it will act. That's up to me completely. But if you want to put minus 8, just put minus 8. It's going to give you minus of this number. Minus 10 to minus 8. What I mean. So negative charge, so the negative is here. So this will be 0.05 squared. Then that is going to give me again the same number, right? 3.6 into 10 power 4 Newton per coulomb, but this time it is minus. So what does it minus mean? The minus means that this force is going to, it's an attractive force. Let's see how it's going to attract. What it's going to do here. Well, if you keep a unit positive discharge, and if this is a negative charge here, it's going to be attracted to that, and the direction is this. Right? Direction is this. So that is my EA2. You see, EA1 is acting in the direction, EA2 is also acting in the direction. It's like this. I keep a positive charge here. This positive charge will repel it, and this positive charge, this negative charge will attract it. So two forces will be acting on this unit positive discharge, and it will go in the direction. Okay. So that's the whole idea of it. So the forces will now get added. Okay, it's not, when they get added, like if you say E, okay, suppose if I take EA, then that is going to be equal to EA1 plus EA2, two vectors now. So that is actually 3.6 into 10 power 4 is the magnitude of EA1, and 3.6 into 10 to the power 4 is also the magnitude of EA2, and they are acting in the same direction. So vectorially when I add, will give me this. So that is going to be equal to 7.2 into 10 power 4 Newton per coulomb. So that's my EA. That's the electric field. Now I know the direction here. So this is the electric field due to these two charges at this point is 7.2 into 10 power 4 Newton per Coulomb. So you may wonder, like you got negative sign here and then you got a positive sign here. If you add those two, then it should be cancelling out. No, it won't. This negative sign simply tells you that this is an attractive force. Okay? But if you just cannot, this is a repulsive force, positive. This negative symbol means it's an attractive force. That is all it tells you. And you also need to see in which direction they repel and attract. And in this case, they are acting along the same line and in the same direction. One is repelling it, the positive number in this direction, and the other is attracting the test charge with a negative number rather in the same direction. So they will get added, they won't get cancelled. Okay, so the positive number just tells you that it is a repulsive force. The negative number tells you that it is an attractive force, nothing more. And once you know this piece of information, all that you have to do is to see the direction of attraction and repulsion. Then add accordingly. Do the addition vectorially. Because they both act along the same line, you can simply add. Suppose one is attracting in this direction and the other one is repelling in this direction, then you just cannot take this number and then say this is a positive number, it's a negative number. You can't just algebraically add. You need to know that, okay, this is attracting in the direction and this is repelling in this direction, so the net force will be in a different direction. Okay? So just because you have a negative number does not mean that you can take that number and algebraically add with another positive or negative number. No, that is not true. The negative number simply indicates that it is an attractive force, nothing else. Okay? So this is how you calculate it for position A. And how would you do that for position B, the point B? How do you do that? Same stuff. What are you going to bring here? You are going to bring a unit positive test charge to this position. Okay? And you are going to see how that unit positive test charge is going to be affected by this charge and also that charge. Okay? That's all there is to it. So let's see how to do that. Okay, unit positive test charge. So first of all, E at B vector is equal to E at B due to 1, charge 1 vector plus E at B due to charge 2 vector. So what you need to do, you need to find the magnitude and direction of this force and find the magnitude and direction of this force, and now add these two vectorially. Let's see. Let's see the magnitude and direction of this force first. I mean due to Q1. So this is positive, unit positive test charge, and Q1 is positive. So what will it do? It's going to, B must be here, right? Let's see. So this is going to repel it first. Okay, so you have positive charge here, there is another positive charge, and this is going to repel it. So the direction of the force is this first. Okay, let's continue now. So I need to find EB1 and also EB2, and then I need to add these forces vectorially. Okay. So again, like I got Q1 here, positive, I'm going to bring a unit positive test charge. This Q1 is going to repel it in this direction. Now I can calculate it, right? So this E B1, what's the magnitude? It's going to be K, Q, 1 to 1 by r square, which is 0.5 or rather 0.05 into 10 power 0.05, sorry about this, square, and that is going to give me 9 into 10 power 9 into 10 power minus 8, so divided by 0.05 squared, which I can write it as a 0.05 squared, and this is the same as this one, right? There's no change in it, same distance, but now the only thing is that the direction has changed. When the unit positive charge was here, this charge was pushing it in that direction, but now when you bring it here, the same charge is pushing it in this direction. When the direction has changed, the magnitude remains the same. So that gives you 3.6 into 10 power 4 Newton per Coulomb. That's fine. Now, what is the magnitude of the force of the electric field due to this charge, the negative charge? We'll do that, right? So E at B due to 2 is equal to, say, Q, KQ2 into 1. I know what's the distance now. It's going to be 0.1 here plus 0.05, so that's going to be 0.15 meters squared. So that is going to give you 9 into 10 power 9 into 10 power minus 8, so divided by 0.15 can be written as say 1.5 into 10 power minus 1 squared. I'm doing it for some purpose, actually, the reason. You'll understand it why it is so. So it's going to be 9 into 10, because 10 power 9 minus 10 power 8 has become just 10, divided by, so 1.5 squared would give you 2.25 into 10 power minus 2. So 9 by 2.25, what do you get now? 9 by 2.25 is okay, 2.25, double 2.25 is 4.5, so you got 9, so twice 4.5, so it's actually 9 by 2.25 is 4, right? So 9 by 2.25 will give you 4, so 4 into, so 10 power minus 2 will go up now, so it will give you 4 into 10 power 3 Newton per Coulomb. So and which direction would it act now? So this positive charge is here, the positive charge is here, the negative charge will attract the positive charge in this direction. Okay, so this was EB1 vector and this is EB2 vector. You see, this attractive force now is acting in the direction opposite to the direction of the repulsive force here in this case. But in the previous case, the attractive force was acting in the same direction as the repulsive force. So you added them. But here you need to subtract one from the other. Which is greater? Obviously the repulsive force is greater. 3.6 into 10 power 4, which is 36,000. And the smaller one, the attractive force is just 4 into 10 power 3, which is 4,000. So you have 36,000 minus 4,000, so we'll have 32,000 Newton per Coulomb in this direction. So effectively, we are going to have a 32,000 Newton per Coulomb, or 3.2 into 10 power 4 Newton per Coulomb. So your EB is actually EB1 minus EB2, which is 3.6 into 10 power 4 minus 4 into 10 power 3, which is equal to 3.2 into 10 power 3 Newton per Coulomb. So 36,000 minus 4,000 will give you 32,000. So Newton per Coulomb. So that is the answer for E at this point. We need to find C now. So we'll do that. Okay, so we have found that electric field at a point A, EA, the value of that was 7.2 into 10 power 4 Newton per Coulomb, and then the value of the electric field at B is to be 3.2 into 10 power 3 Newton per Coulomb. Now I need to find electric field at this point C. So that is what we are going to do now. Okay. Let's see. Okay, so now what I'm going to do? The same thing. I'm going to bring in a unit positive test charge, and that charge I'm going to keep here at this point. Well, so I have a positive charge here, and there is this negative charge, and the positive charge here. So there would be a force of repulsion. So that would be like this. Okay. So this would be E C due to 1. Okay. And what about this? This is a negative charge, a positive charge. It will attract it in this direction. Okay. So this is E C due to 2. So now the resultant EC will be this vector. So that would be EC. Okay. That's all. So what do I say? I say EC okay. So EC is actually equal to EC due to 1 plus EC due to 2. I'm going to add the vectorial. First I need to find the magnitude, and then I need to add them vectorially. So that is what I need to do. Okay, let me find the magnitude. So what is EC1? EC1 is equal to K Q1 into 1, because I'm going to bring the unit positive test charge there. So that divided by the distance is now 0.1. So 0.1 square. Okay. So that will give me what K is 9 into 10 power 9 into 10 power minus 8 and 1. So divided by 0.1 square, which is a 10 power minus 1 square. So you can, so what can you expect from this? So this gives you a 10 power minus 2, this is 10 power minus 6, right? So 10 power minus 2, 10 power minus 8 here, so this gives you 10 power minus 6, right? So 9 into 10 power 9 into 10 power minus 6, so that gives you 9 into 10 power 3, 9 into 10 power 3, so 90,000 Newton per Coulomb. So that is your EC1. And what about EC2? EC2, again K into Q2 into 1 by 0.1 square. Then if you just put the values here, 9 into 10 power 9 into minus 10 power minus 8 into 1 by 10 power minus 1 the whole square. I'm going to get minus 9 into 10 power 9 into 10 power minus 6, the same thing. I'm going to get minus 9 into 10 power 3 Newton per Coulomb. Yeah. But I just cannot add them, right? Because it's plus 9, minus 9. Can I just go and add plus 9 and minus 9 and say 0? No, I cannot. We have discussed it already. It just tells you, the positive symbol tells you that it is it's a repulsive force. And then a negative symbol tells you that it's an attractive force. That's all there is to it. I just cannot add these two without considering their directions. So now the magnitude is the same as this one. The negative sign gives me an extra piece of information that it is an attractive force. But that's of no use to me here. Okay? That's about it. So I'm going to do EC, right? So EC is equal to EC1 vector plus EC2 vector. Okay? Now how do I add them? Okay. You see, it's an equilateral triangle. You got point 1, that's the distance between these two things, these 2 points, and then this is point 1, that's an equilateral triangle. So it's like this now, right? So you have an equilateral triangle. Okay, so this is 60, and this is 60, and this is 60. Now you see one force is in this direction, another force is in this direction. Right? So the angle between those two is 120. Okay? So then the sum, vector sum, is going to be this. Well, you can use the expression C is equal to square root of a square plus b square plus 2ab cos theta, or you can handle things in a slightly different way. Either way you can address this. So the point is, when I do that, the magnitude would be, let's say, what is the magnitude of this? Like E is equal to the square root of EC1 square plus EC2 square plus 2 EC1 EC2 and cos 120. Okay, so if I do this, well, EC1 and EC2 are of the same magnitude. So I'll call that magnitude as, say, A. Okay, I'll call EC1 magnitude of EC1 as A. Okay, so that will give me simply A square plus A square plus 2A square, A into A, and then cos 120 is minus half. So this will cancel. So the minus A square will cancel, these two will cancel, and I will be left with root of A square, and that will give me A, which is nothing but EC1 or EC2. So that gives me this value. So simply, this gives me A, right, which is simply the magnitude of the force is equal to A, which is equal to the magnitude of EC1. So that is 9 into 10 power 3 Newton per Coulomb. So this is easy, is 9 into 10 power 3 Newton per Coulomb. So this is how you do this problem. It's not very difficult. You're going to go from the fundamentals, start finding each and every force, find their magnitude, and then see in which direction they're acting, and add these forces vectorially. Then you can get the answer. So we have done that for 3 positions, A, B, and C. Hope this is clear to you. So now that we have done the problem, let's move on to discuss the next topic. And that next topic is this, electric field lines. You see, if you have a charge, we defined or we described the electric field as the influence of this charge around itself. Okay. So the point is like if we have a charge like this, if we bring a unit positive charge here, then it is going to be attracted or repelled with some force. And if we bring the unit positive charge here, it's going to do the same thing, maybe with a smaller force because we're farther away from it. So there is the influence of this charge here, which is greater, and there is influence of this charge which is smaller here. Okay? How do I pictorially represent this? How do I pictorially represent this? How can I draw a picture to describe it? Meaning that if you look at the picture, you know where the field is stronger and where the field is weaker. By looking at the picture, you should be able to know. So how do we do that? So the way to do that would be this, electric field lines. They are not, as I said, like the electric field lines idea is not something different from what you know already. It's not a separate topic, it's not a new topic per se. We are just expanding on what you already know. The influence of the charge in the space around itself is called the electric field. And how do I pictorially represent this? How can I draw a picture to represent that? That's the question. And the answer to the question is electric field lines. Okay? Well, let's see like the different ways of looking at it. Well, I can probably take this point and then say I can draw a vector, let's say. I mean, here at this point, this unit positive charge will have a force. That will have a magnitude. And it will also have a direction. Right? So I can draw it like this. And then if I take this point, and this point also, the unit positive charge will have a force, but that will be smaller in the direction. So you see, the magnitude is greater here, and the magnitude is smaller here. You see, I'm getting somewhere with this idea, right? So, if I just expand this idea, I have one little catch here. You see, so as I said, like this, it looks kind of broken, but you know that at every point you are going to have some magnitude and the direction. Okay. And it's going to be continuous. If you think about it, like I can draw a continuous line, and again like this I can draw a continuous line, and I can draw a continuous line like this. Okay. Notice here, okay, the moment you see this, look, when you see this picture, you realize that the field is stronger in this region than in this region. Suppose if I divide it into two regions, like if in this region, this is region 1 and then this is region 2. Notice here, in this region, you can intuitively sense that it is stronger, because notice there are many lines per unit length or unit area. In this picture, like it's two-dimensional picture, so if we take this particular length, let's say, okay, let's say if we take this particular length up till here, this length, I take this length, see there are 4 lines in that length. But if I move that length here, you see I've got only 2 lines here, right? So you can see the density of the lines here. Here like you have more lines for the same length, and here you have less number of lines for the same length. So that kind of gives you an idea as to where the field is stronger and where the field is weaker. Clearly the field is stronger here because you have more lines per length, or area. I mean, I've just drawn it in 2 dimensions, but think about it this way. 3 dimension. Okay, this is the charge, and then the lines are going from this charge in all directions now. And if this is the area, you see, if I keep it here, then it's going to cover only a few lines. And if you keep this area here, you see, more lines are covered. Okay, so this is what. So you can say that the field is stronger here, depending on the density of the lines, and weaker here again depending on the density of the lines. So that is what we're trying to say. So you start drawing the field lines like this. Then the question now is, how many lines should I draw? I mean, it's totally up to you. Whether I draw 4 lines like this or 8 lines like this. Doesn't matter. In both cases, for the same length, I have more lines in this area than in this area. Okay, so it's obvious, it's very clear, it's intuitively clear that the more condensed the lines are, the more crowded the lines are in a region, doesn't matter how many lines you draw. Whether you draw 5 lines or 50 lines or 100 lines, doesn't matter. But you can, if the lines are more condensed, more crowded in an area, then there the electric field is strong. The influence of the charge is strong. And if you have less number of lines per area, then there the influence is weaker. So you can clearly see that. So it depends right now on the density of the lines now. Okay, so now you have found a way. It's like, an analogy would be to have a bulb. Okay, for example, if I have a bulb, and if I were to draw so if you were to draw lines, like a light coming out of it, this is how you draw, right? Light coming out of a bulb. So clearly, notice here, the closer you are to the bulb, then the more intense the light is. The intensity will be more when you are closer to the bulb. When you are going away from the bulb, then the intensity will be less. It's a similar idea there. So you take a charge and you start drawing lines for the charge, then you find and you look at the intensity of the lines, electric field lines. These are called as field lines, and if the density of the field lines is more in an area, then the field is stronger there, and the density is less in another area, then the field is weaker there. So that is how you do this. Okay, so this is what is called as electric field lines, simply. So what do they represent? They just represent, it's like the lines are like they give you at any point in space, they give you the direction in which the unit positive test charge will move. So if I have a charge here, Q, and it's going to have an influence around it. Suppose at this point I keep a unit positive test charge, then the electric field line gives me the direction in which that unit positive test charge will move. So the direction is covered by the tangent I draw here, okay, at this point, all these points. And the magnitude of the field would be represented by the electric field line density. If there are more lines in an area, then that area, the influence of the charge in that area is stronger. That's all. Okay? So this is the idea of electric field lines. So by using electric field lines, you represent the electric field. So the electric field is represented by electric field lines. That is the idea. Okay? Now, there are properties clearly for these lines. So what are they? First, suppose I take a positive charge and draw it. Suppose I take a positive charge, it's positive charge. Okay? This is positive. And how will the electric field lines be for a positive charge? Well, if I bring it, what I'm going to do now? I'm going to bring a unit positive test charge. In all cases, my test charge is going to be positive and it's of 1 coulomb value. So, I'll bring a unit positive test charge here at this point. Then what's going to happen? It's going to be repelled in this direction. So you notice here, if you bring it here, then it will repelled in this direction. So the unit positive test charge will repel in this direction. And if you bring it here, then the unit positive test charge will repel in this direction, in this direction, in this direction, in this direction, in this direction. Okay? So note that the electric field lines seem to originate from the positive charge. Okay? So first point is this. The electric field lines field lines seem to originate from the positive charge. Okay, suppose this charge is negative. Let's see what happens. Suppose my charge is negative charge, minus q. Then what I'm going to do? I'm going to bring a unit positive test charge again. So when I bring a unit positive test charge here, this is point, what happens? It will get attracted towards the charge, right? My charge. So it will be like this. And if you bring it here, and it will be like this. So if you keep it here, it will be like this. You see, then if you keep it here, you get attracted like this. If you keep it here, you get attracted like this. You see, all the lines seem to end at the negative charge. Okay? So, electric field lines seem to originate from the positive charge and end at the negative charge. At the negative charge. Well, think about this. Then you said, what is the first part? The electric field lines seem to originate from the positive charge. At the moment you have a negative charge, lines coming in here, meaning that they must have started somewhere, right? And where did they start? Okay, where did they start? Well, you can think of it this way. They start from positive charge or from infinity. They come from infinity, so the positive charge is an infinity. Okay? Because like you got only negative charge here, right? So anything that unit is positive charge, you're going to bring here. It's going to get attracted towards it. Bring here, attract towards it. You keep it farther, it will get attracted. Keep it even further, it will get attracted. See, the line is coming all the way from infinity. Okay, so I can say that the electric field lines seem to originate from the positive charge or infinity. Or infinity. And end at the negative charge. You see, the end of the negative charge. Wonderful. That's the negative charge. That's wonderful. But what of the positive charge? They go from the positive charge, they spread out. Where will they end? Again, at infinity. Okay, so I'm going to use the same thing. Or at infinity. Okay, so that's the first characteristic of electric field lines. And what's the second one? The second point is this. They do not overlap, in the sense they do not cross each other. For example, I cannot have a field like this. I cannot have a field like this. This is wrong. I got white. But what does this represent? What does the line represent? I told you that what is going to happen at that point. Suppose like what is going to happen at this point here? What does it mean? I keep a unit positive charge here, then that is going to be repelled in this direction. That's what the field line means. But now, I'll take the unit positive charge and keep it here. Now you tell me which direction will it go. Will it go in this direction or in this direction? You see, this cannot happen. You keep a positive charge at some point. It can either move in that direction or this direction. It cannot be moving in both directions. So the lines cannot cross each other. So when you draw this picture, the lines can never cross each other. That's a very important point. Okay, the second point is the electric field lines do not cross. They never cross each other. I can't have a line that goes like that. No, I can't have it like this. Because you see, at this point, you have two directions, but only one direction is possible. So, it can never happen. And then the third point The electric field lines are continuous in a charge-free region. So the electric field lines are continuous in a charge-free region. So what does it mean first? Look at this. You have a positive charge. Then for this charge you are going to draw lines. They go in all directions. There is no other charge. So these lines are continuous in a charge-free region. Here, you have a charge here, but there is no charge here, so it's continuous. Continuously going in charge-free regions. Then what happens when you have a charge? What happens when you have another charge here? So let's say I got Q. I'll do this way. Okay, I have trouble, so I'll do it this way. Let's say I have a charge here, plus Q, and then let's say I got a charge here, minus Q. And what will happen? The charge will originate from the positive charge, because we're going to keep a unit positive charge here, right? Keep a unit positive charge, this will repel it, and that will attract it. So the force will be like this, right? E will be like this. So it will repel and attract. So this line will start from the positive charge, end with a negative charge. See? Now there is a discontinuity. And if I keep a positive charge here, then what will happen? It will get attracted to this. And if I keep a positive charge here, it will be like this. You see? Note this. So then if you keep something like this, then if I keep something like this, what will happen here? So this will repel and this will attract. So effectively, I'm going to have this kind of thing, right? Net force will be in this direction. So if you keep it in all these different places, then I'm going to have something like this. Okay? So they'll start from the positive charge, end the negative charge, and then that is how they become discontinuous. So here also it's like that. So it's like that. Okay. Here again it's go in and it will go this way. Okay. So the electric field lines are continuous in a charge-free region. If this charge were not there, this line would be continuous. But because there is another charge, it is discontinuous. Okay. So it's understandable. So that's the third point. So what I've got here, electric field lines seem to originate from the positive charge or infinity and end at the negative charge or infinity, as we saw. Secondly, the electric field lines do not cross each other. It's a very important point, because if they cross each other, which means that at that point you have two directions. That can never happen. You can only have one direction. You keep something there, it gets pushed or pulled in one direction. Okay? So electric field lines do not cross each other. You cannot draw field lines crossing each other. Third, the electric field lines are continuous in a charge-free region. So these are the most important points to consider. Okay? There are a couple of other points also which I'll briefly discuss. One is, they do not form a closed loop. They can't form a closed loop, right? Why? Like magnetic field lines. If you take a magnetic field line, so first number 4 is no closed loops. Okay, like magnetic field lines. So magnetic field lines, if we have a magnet here, then what happens? North and south, and start from north and then it will come back to this, right? They form a closed loop, the magnetic case. But here that is not true. That won't happen, because you take positive charge and then you have got negative charge here. Okay, then it's like that. Okay, it's like that. It's like that. There is no closed loop. There is no continuity here. There is discontinuity there, so there is no closed loop that will happen. Okay, and then pretty much like that's about it. Okay? So these are the 4 points, the 4 characteristics of the electric field lines. One is the electric field lines seem to originate from the positive charge or infinity in this case and end at the negative charge or at infinity. That's point number 1. Second, the electric field lines do not cross each other. And the third one, electric field lines are continuous in a charge-free region. If there is no charge, the lines will be continuous. If there is a charge, the lines will end. There will be a discontinuity there. Okay. Then the electric field lines do not form closed loops. And that is the difference between electric field lines and magnetic field lines. If you remember from your lower standard classes, if you take a magnet, the north-south poles, then the line will start here, then make a complete loop. Okay, but that won't happen here. It will start from positive, end positive. That's it. There are no closed loops. Okay, you see, I can never find a closed loop. You see, it starts from here and it ends here. You see, I can't go this way, not here, because the direction is opposite now. But that is not true in the magnetic case. I go here, I come here, and then again, it's like that. It's a complete loop in the case of magnet. But in the case of charge, I start here, I come here, you see, there is no continuity. The field lines are in the opposite direction now. There is no loop. Okay, so that's the 4th point. So these are the characteristics of electric field lines. To summarize, electric field lines are a mechanism with which we represent the electric field of a charge. The electric field is nothing but the influence of the charge around itself that can be pictorially represented using electric field lines. And the electric field lines at any point, the tangent drawn to that line gives you the direction in which a unit positive discharge will deflect. If I keep a unit positive discharge here, it will deflect along this tangent. If I keep it here, then it will deflect along this tangent. And if I keep it here, then it will go along this. So that is what the electric field lines represent. Okay? And there are 4 characteristics which we have discussed already. Hope this part is clear to you.